Let's talk about a strong acid, strong base titration. And we are going to imagine a very reasonable strong acid, strong base titration scenario. And I'm gonna draw another burette. Now remember, when we're doing a titration, our objective, the purpose of doing the titration, is to determine the concentration of a solution, determine the molarity of a solution that it has an unknown molarity or a concentration that's unknown to us. To do this, we're going to use two pieces of glassware. We've got a burette and then either an Erlenmeyer flask or a beaker. And inside the burette, we are going to fill the burette with one solution. And the flask, we're going to put in a different solution. So we've got two different solutions here. And for this particular example, in our burette, we are going to have sodium hydroxide, which is a strong base. And we're going to make that sodium hydroxide have a known concentration of 0.5 molarity. And then in our Erlenmeyer flask, we're going to put hydrochloric acid, which is a strong acid, and this is going to be our unknown molarity. So for this particular example, our goal, well, for any strong acid base titration, our goal is going to be to determine the molarity of either the acid or the base, whichever one we don't know. In this case, our goal is to determine the molarity of the HCl. So we're going to determine the molarity of the HCl. The way that we're going to do it is by reacting the sodium hydroxide with the hydrochloric acid. So what we will do is we're going to open up the stopcock on the burette, and we're going to allow the NaOH solution to drip down into the hydrochloric acid solution. And as the NaOH drips down into the hydrochloric acid solution, they're going to react with each other. So let's think about what that reaction is going to look like. NaOH, which is a strong base, is going to react with HCl, which is a strong acid, so it's going to be a forward reaction, not equilibrium. It's an acid-base reaction, so the cation sodium and the anion chloride are going to combine together to make NaCl. And then also the OH and the H are going to combine together to make water. So we have a very predictable reaction here. So as the sodium hydroxide comes down into the hydrochloric acid solution and the NaOH and HCl mix together, they're going to be producing these products inside this Erlenmeyer flask. We are going to add sodium hydroxide from the burette into the flask until we have completed this chemical reaction. So we are going to add enough NaOH, and we're going to add just exactly enough, not too much. Exactly enough NaOH to react completely with the hydrochloric acid. Again, not too much. We're going to add just enough so that we get a total reaction. So that would mean, let's say, I'm going to rewrite this equation. NaCl plus H2O. Let's say that if we had 5 moles of hydrochloric acid down inside of our flask, our goal would be to add exactly 5 moles of NaOH so that they could react completely without any leftover HCl, no leftover NaOH. If we had 10 moles of hydrochloric acid in our flask, we would want to add 10 moles of NaOH. And you get the idea. We want to have exactly enough of the acid and exactly enough of the base that they react perfectly and completely with nothing left over at all. So how are we going to know when we've added enough NaOH to react with all the hydrochloric acid? Because the hydrochloric acid is unknown, this whole idea of, let's say we have 5 moles, okay, that means we need to add 5 moles of NaOH. We don't have that kind of information. We can't make that type of calculation because we don't know anything about the hydrochloric acid solution. So how are we going to figure out when the reaction is done or when we have met our goal of adding exactly enough NaOH? And we're going to do that by monitoring the pH of the solution. We know, even though we don't know how much HCl is inside of our flask, how many moles of HCl are in the flask, we know that HCl is an acid, and therefore we know that it has a pH that is something less than 7. So we could put a pH meter inside that hydrochloric acid solution, and it's going to give us a number that's something less than 7. We know that our sodium hydroxide is a base, which means that it has a pH of greater than 7. We're not going to put a pH meter up inside the burette because A, it's not going to fit, and B, having just one pH meter is plenty. We don't need to have 2. As NaOH and HCl react, they're going to produce sodium chloride and water is neutral in terms of its pH, so its pH is equal to 7. And NaCl, if you remember back to where we were talking about the pH of ionic compounds, of salts, acidic and basic cations and anions, NaCl is a neutral ionic compound, so it also has a pH of 7. And so this is going to help us monitor the progress of the reaction. Initially, before the reaction starts, the flask, which is just full of HCl, will have a low pH, something less than 7. As we add sodium hydroxide down into that flask and the sodium hydroxide reacts with the HCl and starts using it up, so during the reaction, the pH of the flask is going to start to go up. So this is going to be the flask of HCl, and now we have some NaOH mixing around in there, and they're making products. The pH of that is still going to be less than 7, but it's going to be going up. So it's going to be higher than our initial pH. It'll be rising as we add more and more NaOH. The pH is going to get higher and higher and higher. When we get to this point where we have added exactly enough NaOH to react completely with all of the HCl, when we have no more NaOH, and therefore we have no base, and we have no more HCl, and therefore we have no acid, all that we have left in our flask at that perfect moment is just these 2 guys right here. So at the exact perfect point, which we call the equivalence point, the pH in the flask is going to be equal to 7 because it's going to be perfect. Now, if we were to keep on going, I'm going to put my reactants back over here. If we did not follow this rule of add exactly enough and we kept on going and added more NaOH, so this would be after the equivalence point, our flask is going to have a pH that is above 7, greater than 7, because we'll be adding more of that NaOH, which is a base, which has a high pH. So what we're going to do up in our Erlenmeyer flask is we're going to monitor the pH, and when the pH reaches 7, we'll know that the reaction is done. We'll know that everything is perfect, and we will stop the burette, we will stop adding solution, and then we're going to take some data measurements. Before we continue on, I want to let you know that this equivalence point is sometimes called the end point. So those two terms are used interchangeably, and they both mean the exact same thing.